All right, let's dive in. Today, we're going to crack the code on the anion gap. It's a remarkably simple calculation that can uncover some serious, life-threatening problems that are often hiding behind what looks like a perfectly normal set of labs.
So let's start with a really important question. Can a set of labs come back looking completely normal, totally fine, and actually be lying to you? Well, as we're about to see, the answer is a huge yes. And figuring out how that happens is the key to this whole thing.
Okay, let's set the stage with a patient case. At first glance, everything seems pretty straightforward, but there's a big twist hiding in plain sight.
So here are the initial numbers from our patient, who has a history of alcoholism and has been vomiting. The pH is 7.40, the PaCO2 is 40, and the bicarbonate, or HCO3-, is 25. I mean, look at those values. Every single one is smack dab in the middle of the normal range. So, case closed, right? Everything's fine? Well, not so fast.
This is where we have to put on our detective hats. Those normal blood gas values, they're actually a distraction. The real clue isn't something that's measured directly on the report. Nope, it's something we have to calculate. We need to go looking for the unmeasured anions. And the tool we're going to use for this is the anion gap. It's really just a clever calculation. It gives us a window into all the negatively charged things floating around in the blood that the lab doesn't bother to measure routinely. Stuff like proteins and phosphates.
The easiest way to picture this is with a balancing scale. Your body wants to be electrically neutral. So, on one side, you have all the positive ions, the cations. On the other side, you have the negative ions, or anions, that we actually measure. For it all to balance out, there's always this little leftover space, this gap, made up of those unmeasured anions. But the real story begins when that gap gets a whole lot bigger than it's supposed to be.
Okay, so enough theory. Let's actually put this tool to work. We're going to take our patient's labs and calculate this hidden clue ourselves to see what's really going on behind that normal facade.
And you're going to love how simple the formula is. Seriously, you just take the main positive ion, which is sodium, and you subtract the two main negative ions we measure, chloride and bicarbonate. And that's it. Whatever's left over, that's your anion gap.
All right, here are the numbers we need from our patient. We've got a sodium of 135, a chloride of 80, and that bicarbonate that looks so innocent at 25. Now we have everything we need.
So let's plug them in. We take 135, and we subtract the sum of 80 plus 25. So what does that give us? This right here, this is the moment the whole case just cracks wide open.
30. Wow. Our patient's anion gap is 30. And that single number just completely shatters the illusion of those normal labs. But just how high is 30, really? Let's put it in perspective.
Okay, so a normal anion gap is usually somewhere around 10, maybe 12. Our patient's is 30. That is not just a little high, it's nearly 3 times what it should be. This is a massive flashing red light, telling us something is seriously wrong under the surface.
So we found our clue, a huge anion gap. But wait a second, this just creates a new puzzle, right? If the patient has a high gap acidosis, why on earth were their blood gases, especially that bicarbonate, totally normal? It's time to solve this mixed disorder.
This is the million-dollar question. An acidosis, by definition, means there's too much acid, and that acid should be chewing through the body's bicarbonate. That number should be low, but ours is 25, right in the normal range. How is that even possible?
And here's the elegant and kind of scary answer. Our patient doesn't have one problem, they have two, and they are fighting against each other. The vomiting is causing a metabolic alkalosis, which is raising the bicarbonate. At the exact same time, their history has led to alcoholic ketoacidosis, which is lowering the bicarbonate. These two opposing forces are basically canceling each other out, creating this deceptive normal value right in the middle.
We can actually put some numbers to this. It's a concept some people call the delta-delta. Just look at the change from normal for both values. The anion gap went from a normal of about 10 up to 30, so its change, its delta, is 20. But the bicarbonate, it went from a normal of 25 to, 25. Its change is 0. That huge discrepancy of 20, that tells you exactly how much hidden acid was being covered up.
So here's the bottom line. The only reason we found that potentially life-threatening acidosis was because we calculated the anion gap. It was the only tool that could see through all the smoke and mirrors of this mixed disorder and show us the real danger.
Okay, now that we've seen it in action, let's give you a quick toolkit to use.
When you see a high anion gap, what are the common culprits you should be thinking about?
Well, the classic mnemonic, and it's a classic for a reason, is MUDPILS. This is your go-to list. It covers everything from toxins like methanol and ethylene glycol to really common emergencies like diabetic ketoacidosis and lactic acidosis. It is an incredibly useful way to build your differential diagnosis in a hurry.
You know, if you only take one single thing away from all this, let it be this. An increased anion gap means there are hidden acids in the blood. It's really that simple and that important.
And that really brings us to our final thought. Today's case is just a powerful reminder that sometimes the most reassuringly normal number on a lab report can be concealing a pretty dangerous secret. It challenges all of us to always think a little deeper, to look for those hidden clues, and to always be asking what other normal values out there might be hiding a much deeper story. I'll leave you with that.